Okay, it's recording.
Mhm.
All right. We'll just start from the beginning and jump in if you have any questions, okay?
Okay.
Okay, so first off, we're going to talk about probability, the definition. And that is the number of ways to, I'm just going to be real casual here, to get what you want over the total number of ways that the experiment can be done. Okay, so when we're thinking about probability, you're going to always assume you get what you want. So like if you have a deck of cards, then you always assume that, you know, if you want the probability, say, of a 2, you always assume you're going to get a 2. Okay, so you count the number of ways that you could get a 2. So I'm going to just start out with this example. Let's see, I want to make sure I cover everything. So I'm going to get my notes here. All right, so I did the definition. Mutually exclusive. I think we'll do that first. Just means they can't happen at the same time. So actually, it's one event can't happen at the same time. So for two events to be mutually exclusive, they have to be separated. I'll draw a picture. There's two sets. So if you had, like, we're going to do an example where you have red balls and you have blue balls. So if you had, or we could do like red or green. So if we have red balls and a green ball, you can't, and you're picking one ball, you can't pick red and green at the same time. So those are mutually exclusive.
Okay.
But if you had, say, a face card in a 52 deck of cards, 52 cards in a deck, okay, a face card, and say a red card. No, that's not. And a, say, 10. Okay, so the no, I was right. I have to get my thinking cap on. Red card. We'll do red card. See, those overlap because so those would be not mutually exclusive.
Okay.
Because you could have like a jack, queen, and a king that are diamonds and hearts. Those are the red cards. So you can have red cards that are face cards. So they would overlap. So mutually exclusive are two outcomes that can't happen at the same time.
Makes sense.
Okay, so I'm gonna add a page. All right, here's another example, say, face card. And 2. So face card and a 2 would be mutually exclusive. The face cards are just jack, queens, and kings. But if you had, here's another example, face card. And let's say clubs, those overlap also because you could have in here the jack, queen, king of clubs. They can happen at the same time. So these are not mutually exclusive. So another way to say that is the probability of A and B should be 0 if they're mutually exclusive. That means impossible. So when the probability is impossible, the probability is going to be 0. That they can't happen.
Okay. So 0 means that they cannot happen.
Yeah, 0 is impossible.
Okay.
That brings us to probability of an event. So I'll just say probability of an event is always between 100%, which is 1, and a 0. So it's always positive, and it's always a fraction or a decimal between 0 and 1. If it's 1, that means it's certain. It's going to always happen. That's 100%.
I'm not seeing what you're typing anymore on the screen.
Oh, you're not? I guess I went down too far. Okay, let me. I'm not sure how it says I can only have 12 pages and I need more than 12 pages. So I'm not sure how to do this. I'm just going to erase it. I haven't used this, so it's going to take me a while to figure it out. Okay, so can you see the probability of an event is always between 1 and 0. So 1 is 100%. That's certain, no matter what happens. Like if you had a box of only red balls, and I ask you, what's the probability of getting a red ball? Well, that's 100%. You're going to get a red ball. But if I ask you to get a green ball, there's no way you could do that because they're all red. So that would be 0. That would be impossible.
Okay.
And so probability is always a fraction between 0 and 1, or a decimal between 0 and 1. So you'll never have a probability of 2, say. You'll never have a probability of a negative number. Okay, let me check my email real quick, see if anybody else was trying to come on and I can give them this invite
Okay.
real quick. No, I don't have anything. So I'm recording it so they can watch it. Okay, so does that kind of answer your question? Maybe
It does. Yes.
Yeah. Don't think more than that. There's nothing more to it than that.
Okay. Again, I was overthinking it. Okay. Because it seems so simple now. I was like, is that it?
Yeah, because some of it can get, more in, difficult.
Mhm.
And probability is pretty challenging and you're learning it in a week. So that's why I just want to kind of concentrate on the stuff that you're going to use
Okay.
this week. Okay, so the next thing is I'm not sure how I can erase this whole page.
I was able to go down to and look at the pages. So I see what you did up to, when you did the formula in less than -1 and 100% certain. I see all that now. So I don't know what you did, but I was able to scroll down and see the
Huh.
next pages.
Okay. I'll just keep using new pages until they say I can only have 12 pages and then I'll start erasing, I guess, or
Mhm.
just make a new whiteboard. So let me go ahead and we'll just do another page. And so let's talk about the word or. So the words we're going to use here are or and and. Okay, so or this is if we have like one event. So I'm going to start out with nine balls for my example, and they have numbers on them. So they're numbered 1 through 9.
Mhm.
And the first 4 say are red, and the last 5 are green. And you can't see what you're going to pick. Okay, so they're in a box. So if I just say, what's the probability I pick a red? I don't know. I think it's doing that because I'm putting my whole hand on the screen. Okay, there we go. What's the probability we get a red? So remember the definition of probability. It's the number of ways we can get what we want divided by the total number of outcomes that are possible. So the chances we get a red, there's 4 reds, 1, 2, 3, 4. So there's 4 ways to get a red. And then there's 9 ways to just pick any ball because there's 9 balls.
Okay.
So this would just be for that. This would be basic probability. Okay, just the one answer. I'm picking one event. I'm picking one ball. So my event is choose one ball. So just because I'm picking one ball, a lot of mistakes are made by thinking, oh, it's just going to be 1 out of 9. But no, you have to think that you're going to get a red, and you have to think, how many ways can I get that red? Well, there's 4 reds in that box, so there's 4 ways that I can get a red. Now, what if I said, what's the probability that I get a 1 or a 7? Okay, so I'm using the word or. 1 or a 7. So the word or would mean add. So you would break it apart and just say, count the ways that you can get a 1 plus count the ways that you can get a 7. So how many ways can you get a 1?
1.
1, good, because there's only 1 1. So 1 out of 9, because there's 9 total. Now move on and we start the whole experiment again. So how many ways can you get a 7?
Let's see. 3 plus 4, that's
Well,
1.
but we're only picking one ball.
Oh, one ball. Oh, with one
We're
ball.
only picking one ball. So, I
Oh,
mean, that's a good way to think. If we had 2 balls, yes, you would have to, it would say how many ways to get a sum of 7.
Oh,
But
okay.
right now, we're just gonna stick with picking, well, later on tonight, I'll pick 2, but right now we're just picking 1.
Okay, so then that would be 7 as well. Well, I mean 1, because
Yes, there's
Yeah.
one way to get a 7,
7,
so that
yeah.
would be 1 as well, right? 1
Mhm.
out of 9. So you just add the numerators and that would be 2 out of 9. Okay, so the reason you can do that is because those are mutually exclusive. Here's the chances you get a 1. Here's the chances you get a 7. You can't get both at the same time. Those are mutually exclusive. Because you can't get a 1 and a 7 with picking one ball. Now picking
Mhm.
2 balls, yeah, but we're not picking 2 balls.
Okay, got you.
Okay, but what if we asked, what's the probability? Again, we're picking one ball of getting a red or an even number on the ball. Again, this is or, we're only picking one ball. So are those mutually exclusive?
Ooh. Mm,
The even numbers
No,
are 2, 4, 6, 8. Right, they're not,
no,
because you can get a red 2 and a red 4.
4, right.
Right, so these two sets, a red and an even, overlap. So these are not mutually exclusive. So we have to worry about what's in here. Okay, so we don't count anything twice. So the formula that we're going to use is probability that is red. So we're going to count all the reds.
Mm-hmm.
We're going to count all the evens. Again, or means add.
Mm-hmm.
But we're going to subtract out one of the cases where it's red and even. So I'll write this formula down after we do this problem. But what you're doing is when you count all the reds, you're counting everything in here. When you're counting the evens, you're counting everything in here. So you're counting this middle twice, and we only want to count it once.
Okay,
So that's why we have to subtract one of those out.
makes sense.
Okay, so the chances you get a red, well, we already did that. There's 4 reds. 4 reds out of 9 total. Chances you get an even number. Now we don't care what color this is even. So it could be an even number is 2, 4, 6, 8.
Mm-hmm.
So there's 4 ways that you can get an even number. Because it doesn't say even red, it just says even.
Even. Okay.
And then we subtract the ones that are red and even. Well, that's 2 red and a 4 red. So that would be 2 out of 9. So when you add the 8 minus 2 is 6, and you can reduce that and make it 2/3, or you could change it to a decimal.
Okay.
All right, so the formula that you're going to use for this is for probability of A or B, okay, with one event, you're picking one ball, one card, just you're picking one thing. So the probability A or B is, or means addition.
Mhm.
And you can stop there if they're mutually exclusive, if they don't overlap. If they do overlap, then you have to subtract out one of those overlapping pieces. This and means both at the same time. And if they're mutually exclusive, remember that and is 0. So that's where it goes. So if they're mutually exclusive, the probability that they overlap is 0. So actually you're using the formula all the time. It's just that end part just doesn't show up if they don't overlap. So or means add. Then I'm going to talk about complement. So the complement is the probability that something doesn't happen is 1 minus the probability that it does happen. And that's really easy to see, okay? Because if you think of 1 as 100%, so if we draw a picture here, we have A or we have not A. And this whole thing should add up to 1 or 100%. So the probability of this happening right here, not A, would be 100% or 1 minus probability that A happens. So that's why it's called the complement, because they're opposites. So I can just do a real easy example with those balls. I could say the probability that it's not red, again, you're just picking one ball, is 1 minus the probability that it is red. And that was 1 minus 4/9. So the way you could do that, you can use a calculator, but it's 9/9 minus 4/9. And oh, what happened? Well, I don't know how that happened. Where'd it go? All right. Well, anyway, I'll continue on. So 9/9 minus 4/9 is 5/9, which was probability not red. But probability not red is probability that it's green in this problem. And if you notice, 5 balls were green, we had 5 greens over 9 total. So it works out, just so you know. So that would be the complement. And go ahead.
No, I was saying, oh, okay. So,
Okay.
okay,
The way also that you would use this is, suppose you have, well, like you have 1, 2, 3, 4, 5, say on cards, the probability that, let's see. Let's see. I'm gonna think about that for a minute. I'll come back to that when we do like pick more than 2. I'll come back to that example.
okay.
I want to go back. I want to go and talk about and now. Okay, and has 2 meanings. And it just depends on whether you're picking 1 or 2 things or more than 1 thing. Okay, 1 event. If you're talking about and with 1 event, it's both at the same time. And we've already seen that. So it would be red and even would be a red and the 2 and a red and the 4. That would be, those would be those outcomes. So red and even would be red, the red ball, which was a 2 in our example, or it could be a red ball that was a 4, because the first 4 were red and then the 5, 6, 7, 8, 9 were green. So that would be both at the same time. But if it's 2 events, 2 or more that you're talking about, then and means multiply. So or means add and means multiply if you're talking about 2 or more things. And there's 2 ways you can do this. You can do it with replacement or without replacement. So with replacement means you pick one, put it back. Without replacement means you pick one and you keep it. So you keep it out of the box. Okay, so let's see. All right, we have the example 1, 2, 3, 4. Those were red balls. And 5, 6, 7, 8, 9 were green balls. And we're going to pick 2. Okay, probability, we get 2 green balls. And we're going to do it with replacement. And we're going to do it without. And then we're going to talk about independence, because that's what this is. Okay, so with replacement. Okay, so I like to do it kind of like a fill in the blank. So you have two balls, so you have 2 blanks, and means multiply because you want a green and a green. So again, if you have two or more events, then the and means multiply. But if you only have one event, then and means both at the same time. So you don't, there's nothing to multiply if you're just picking one thing. But if you're picking two things, then we want a green and a green. So the chances that you get a green on the first pick with replacement doesn't matter on the first pick. So there are 5 ways to get a green out of the 9 balls. Now the difference here is with replacement, you get a green, you assume you get a green, and then you put it back in the ball box and you mix them all up again. And so you still have 9 balls. So a total still 9, and you still have 5 ways to get a green. But without replacement, okay, this is starting the experiment over again. So you still have, you have 5 ways to get a green ball. There's 5 green balls out of 9 balls. And so that means multiply. You want a green on the second pick. But what happens here is you're going to keep it. So without replacement, you got a green ball. You only have 8 left on your second pick. You only have 8 balls left because you kept it. And you got a green. You always assume you get what you want. So out of those 5 greens, so go ahead.
No, that my daughter just walked in and started talking.
Oh, okay, that's fine. Okay, and then it's 1 less. So you have 4 greens left to choose from because you got a green on the first pick. So that would be 20 out of 72. Or 10 out of 36. Or let's see, we can reduce it 5 out of 18. So does that make sense? It'll go down by 1.
Yes.
So that's the only difference about with replacement and without replacement. With replacement, it's just like you're starting all over again. Your total remains the same, but without replacement, it's going to go down by 1 each time because you got what you want and you kept it out.
Okay. Okay.
All right, let's see. I want to make sure I talk about everything. Okay, well then that brings us to conditional probability. And I posted today because I looked at some of the discussions and they were good, great discussions, lots of really good improvement. And but this is where it was catching people up. So I hope this will clear it up. Conditional probability. Okay, so that looks like this. The symbol you'll see is a slash. Okay, so that's supposed to be just a straight line. And that is read, you read that as the probability that A happens given B happened. So it gives, this given means it's a condition. This part right here, this given part, this last part is the condition. So it's called conditional probability. Okay, so in our example with the red and the green balls, let's say, what's the probability that we get, let's say, an even number given that it's green? So this is always the condition. So we know it's green, given the given part we know, given it is green. So it's not coming out of the nine things anymore. Okay, this part right here, when you have a given, it's going to make our sample space smaller. Because now we know where it's coming from. So it could be, you know, given that you're blonde, or given that you're tall, or given that it's an odd number. It could be, you know, anything like that. The given means that we know that it's coming out of that set. So given that it's green, we know it's green. So it can't be 9 anymore. So there's 5 green balls. So 5 is going to be our denominator. So the given part is going to go in your denominator because it's not 9. We know it's green, so that can only be 5 out of the 5. What's the probability that it's even? So even in green, let's see, it would be the green, it would be a 6 green or an 8 green, because the green ones were 5, 6, 7, 8, 9. So 6 and 8 are the even numbers. So there's only 2 that are even and green. I don't know what it's. So it's giving green. So the formula that we're going to use for this is the probability of A given B is the probability of A and B at the same time over the probability of B. The given is always in the denominator. So, and we can do another one. So again, let me write that formula down. Probability of A given B is the probability that A and B happen at the same time over the chances B happens. So let's try probability that it's green given that it's odd. So again, the odd, given that it's odd, is the second part is always the given part. So we know already that it's odd. So we know something about this. So it's not out of the 9 anymore. It's out of the ones that are odd. So we have, which are odd. We have 1, 3, 5, 7, and 9. We have 5 ways to get an odd number. 1, 3. Again, this is still our ball problem. So there's 5 ways to get an odd number. The numerator would be, what are the which ones are green and odd? Well, that would be the 5, the 7, and the 9, because the reds were 1 through 4. So there are 3 ways to get a green and an odd, and that would be in the numerator.
Okay.
Or you could do, we'll do one more. Probability, it's red, given, it's even.
Mhm.
So the even number of ways you can get an even number would be at the bottom, and red and even would be on top. So evens are 2, 4, 6, and 8. Our balls were 1 through 9. So there's 4 ways to get an even, and just the 2 and the 4 were red. So those were the red ones. So there's only 2 ways to get a red and an even at the same time. So just remember, when you have the word given, it makes your sample space smaller. It's not coming out of the 9 anymore. Because
Okay.
you know something more about it. It's coming out of the given part.
Oh, gotcha. Makes sense.
Okay.
Okay, I saw where you posted on one saying, look at given. You have to
Yeah,
keep it.
make sure there's just one question on the discussions.
Mhm.
And it may, and this is what I was talking about. And see if that helps. If it doesn't help, just contact me and I'll explain it further.
Okay.
But just, yeah, watch out for that word. And there's also an easier way to do this. Well, and they give you a table, so I think you'll have this in the Connect exercises. So let's talk about this. I guess this is a good time to talk about independent. So mutually exclusive is pretty easy to draw a picture for. You can draw out like your sets, and if your sets overlap, then they're not mutually exclusive. Or if they intersect. If they don't intersect, if they stand on their own, then that's mutually exclusive, and that's like with one event. Okay, with independent events, you have to have like 2 events. So that's another way to 2 or more. So if they're independent, there's 2 definitions you can use. The definition would be, and I like to use this one, so I'm just going to use this one. Probability of A given B is equal to the probability of just A. And this should make sense. This definition makes sense to me only because, again, this is the probability of A given B is the same as just the probability of A. Well, then that means B has no effect. So there have to be independent.
Okay.
So if you just like cross out B, you have the probability A equals probability A, and that makes sense. So B has no effect. So here's a simple example. Suppose I give you numbers, and this is what they'll do in like your homework. They'll give you a problem, and they'll say the probability that A happens is 0.35. probability that B happens is 0.4, and they don't even have to tell you what A and B are. And the probability, so they're just giving this in an example. They're just giving us these numbers. So we may need some more information here. Let me see. So we're going to test the probability of A given B is going to be the probability of, I'm just going by the definition of conditional probability. So it's the and on top and the B goes on the bottom. So we're going to see if these are, if A and B, we're testing to see if A or B are independent or dependent. So we start with the definition of, we're going to use this side right here. So we're going to start with the definition of that, which we just learned. And then we fill in our numbers. Well, we know the and part is 0.12 and the B is 0.4. And when you divide those two, you get 0.3. But that's not equal to the probability of A, which was 0.35, that they gave us that, okay, here, they gave us 0.35, and those two things aren't equal. So these are dependent. Well, let me just talk about, I don't want to confuse anybody. This is just an example that they made up and they gave us this information. Okay, so they just went down the line and they gave us the chances of A happening are 35%, chances B is 40%, and A and B at the same time is 0.12 or 12%. So we're trying to prove that either that this is equal to this is what you're trying to prove. If they ask you, are these independent events or dependent events? So we're starting on this side, the given, and we use the definition of A given B is A and B divided by B. So we use the fact that A and B is 0.12 and that B is 0.4, and we fill in the blanks. So that's going to go there. This is going to go there. And when you use your calculator, it's 0.3. But then you can see from here that they're not equal because they gave us that number. Those two numbers aren't equal. So that tells us that A and B are dependent.
Okay, when they're not equal, they're dependent.
Right.
Okay.
When they're equal, they're independent. Because look, if they're equal, then we can just say, we can just cross out this B and B doesn't have any effect. Probability A is probability A. So when they're equal, they're independent.
Okay.
All right, then you'll have like a table problem. So my table, okay, we did a survey and they asked men and women what their superpower was. So I picked this example, superpower. Would you like to fly or would you rather be invisible? So you're gonna have this table and I'm just gonna show you how to use it.
Okay.
And yours, of course, is going to be a different scenario, but same thing. So you're either male, female. So the number of males that said they wanted to fly is 26. The ones that are visible is 12. 12 females want to fly and 32 females want to be invisible. I don't know. I think I'd rather, I don't know which one I'd want. Have to think about that one. But anyway, okay. So what I would do first, when you get this table or see any table, what I would do is just start adding up the totals. So when I add down here, I get 38 males. So when you add down, that's going to give you the total of males.
Mhm.
When you add down here the females, you're going to get the total females, 44. When you add across, you get the total of the people that want to fly. So that would be 38. You add horizontally, and invisible would be 44 also. And so, and that's not always true. Those aren't always the same. This is just a fluke. Maybe I'll change the numbers just so that they're not the same.
Mm.
So it won't be confusing. Let me make this,
Did you hit next page? I didn't see the next page pop up.
yeah, I did.
Oh, there we go. Okay, there it goes. No, it didn't come up at first. There we go.
Oh, I'm sorry. Do you see it now?
I see it. Yes.
Oh, I'm sorry. It must take a while then, because when I write, sometimes it's lagging behind. So all I'm doing is I changed one of the numbers so that they weren't the same. So all I'm doing is adding across and adding down.
Okay.
And then when you add this way and add down the final numbers, they should be the same. So when I add down, that's 81. And when I add horizontally, 43 and 38 is also 81. So this is the total number surveyed. So altogether, we surveyed 81 people.
Mm-hmm.
That's what that is. All right. So how do you use this? Well, they're going to ask you, are flying and males independent? Just say flying. We're going to test to see if flying and males are independent. So we want to find the probability that you want to fly, given that you're a male. And we want to find the probability that you just fly, that you want to fly. And if those are equal, then they're independent.
Let's see. So we look at the total that want to fly and then the total of male that want to fly.
Yes, very good.
Okay.
So let's do the total of who want to fly because that's easiest. So total who want to fly is 37. So the people that fly total is 37. "37 people want to fly out of 81 people that were surveyed." Okay, does that make sense?
Yes.
Okay, so you just read across total flying,
Mm-hmm.
total people, because there's no condition on that one. So since there's no condition on the second one, it has to come out of the whole total. Now this one would be, we use the formula fly and male. So the males who want to fly over probability that you're a male. So how many males want to fly?
26. Is that
Yep.
26? Yep.
Yep, male fly. You just read it in the chart, 26
Mhm.
over the total males.
Then total males is 38.
Yeah, very good. So if you took a calculator, you can see that those are not equal.
Mhm.
So those two things are dependent.
Okay.
Let's do one more just to make sure. I got it. Using this chart, we want to find out if being a female and wanting to be invisible are independent. So let's find the probability that you're a female, given that that you want to be invisible. And the probability that you're a female. See if these two things are independent.
Okay. So female indivisible. That's 32 over, would that be over the total female population or the total population?
Okay, careful. If we're doing the first one, you
Mhm,
were right with the numerator.
mhm,
Invisible female is
Right.
32.
mhm.
So this is female and invisible.
So is that a given because it's only talking about female and invisible?
It's a given because it's only talking about invisible people, the
Okay.
people that want to be invisible. So
Okay,
this is the given part.
okay.
So it has to come out of the people that want to be invisible.
Be invisible. Okay, so then that would be over the 44.
Yes, very good.
Okay.
It'd be over the 44. So the second part always goes in the denominator.
Gotcha.
So invisible, there's 44 total. So invisible is 44, and that is the given. All right, so what are the chances you're just a female with no condition?
So that's going to be the 43 over the, what's that number? 81?
Yes, very good. And if you use your calculator, those aren't equal. So female and invisible are dependent. So if they're not equal, they're dependent.
Dependent. Gotcha.
So you'll see one of those in the Connect exercises. If you have any questions, you can let me know about that.
No
And
questions.
if you have time, I want to do one more thing.
Oh, I have time. Nope,
Okay.
I have time.
Okay, let's talk about factorial. Okay, this is counting. So we have to learn how to count actually before we do probability. So let me do an example first and then I'll talk about the definition. So let's suppose we have, I'm going to do a real simple one, apple, orange, and a banana. Okay, so how many ways can you arrange those on your countertop, say. So we could, and this is not probability, we're just counting the ways. How many different, that's a key word there, different arrangements. So you just have one of each. So you could have apple, orange, banana. You could have apple, banana, orange. You could have banana, orange, apple, banana, apple, orange. Or you could have orange, apple, banana, orange, banana, apple. So if you're counting different arrangements, there's 6 ways.
Okay.
Now to do that mathematically, because how about if you have 100 things you want to arrange? We're going to do, I like to call it fill in the blank. And oh, by the way, you're only going to really use this. Well, no, this is in Connect. So you are going to use this in Connect. Okay, so that's why I'm covering it. All right, so you have, suppose you have 3 spots. So in the first spot, you can choose any one of the 3. So you have 3 ways to fill the first spot. It could be an apple, orange, or a banana. But once you pick one, okay, like if you pick the apple, then you only have two ways left. And notice I'm using and. So I pick one fruit for the first spot, and I pick one fruit for the second spot. And then there's only one way left to fill the last spot. So the word and again means multiply, but if you multiply 3 times 2 times 1, that gives you 6. So that's how you can do that. That's called factorial.
Oh, okay.
So we write it with 3 and an exclamation point. So that exclamation point means factorial. So suppose, just for an example, if you want to do, say, 8 factorial, what that means, that's just shorthand. It means start at 8 and just multiply, go down by 1 each time and go all the way down to 1. So 8 factorial would be 8, 7, 6, 5, 4, 3, 2, 1. So you can see why we need a shorthand, because you don't want to write that out all the time. So that's what factorial means.
Okay.
And it's the number of ways. So like, let's say n factorial, where n's any number, the number of ways to arrange n objects in order. So the order part matters. Because if we were going to say this had no order, so how about if this just had no order? We have 3 pieces of fruit, and we just want to make a fruit salad, say. We're just going to throw them all in and mix them up together. Then they're all the same. Like apple, banana, orange is equal to orange, banana, apple is equal to apple, orange, banana. They're all the same. So there's only one way. No, if there's no order here, it's all the same. So the n factorial is if there is order, if there's no order, there's just one way, and we use this fancy formula called a combination. So combination is when there's no order.
Okay.
And we use it for, it's really easy to remember because that starts with the C. And so if we're playing with a deck of cards, they don't have order. You can put them in any order you want and you still have the same 5 cards. So with a deck of cards, with committees, with C words, if you're just picking like 5 people to be on a committee, there's no order there. You're just picking anybody. So there's some examples, deck of cards, picking groups, committees. But if you're picking people like to go to bat, if you were in a baseball and you had say 9 people, how many ways can you line them up? Then that would be order because you're lining people up.
Right.
So there's some keywords that you look for.
Okay.
But the reason I wanted to do combinations is because they're part of, let's see, the binomial distribution, which I did a whole video on that, and it's not too long, so I'm gonna let you watch that. But the formula for a combination, now some books use that and other books use this notation. They're the same. It's the number of ways to choose R objects out of N with no order. Okay, so no order. And the formula goes like this. So we put N on the bottom. Yeah, no, N on top, sorry. N on top, N minus R on the bottom, factorial, and R factorial. So we have 3 factorials here. So an example of this, again, would be committee. So we have 10, suppose we have 10 people. And we want to choose 4 to be on a committee. Now, if you were going to say, oh, you're going to pick them to be president, vice president, and a secretary, and you're giving them actual positions, then this would not be a combination. But we're not going to deal with that in this class. Okay, so your problems are going to have no order. If we pick somebody just to be in a group, then we have no order. So this would be C10, 4. We have 10 things and we want to choose 4. So you put the 10 on top. The 4 on the bottom. And then you subtract 10 minus 4. So that would be 10, 4, and 6. And this is really nice. Watch what happens. It's really nice. We do 10. Remember, factorial means go all the way down to 1.
Mhm.
Four. Go all the way down to 1. And 6, start at 6. And go all the way down to 1. I don't know why this isn't writing good. Okay, watch what happens. That's going to cancel. So that always happens in these problems. And then you can do some other canceling. Let's see, maybe I can, yeah, I can use different color. So I can do the 4 times 2 is 8. That'll cancel with the 8. Or you can just use your calculator and work it out. But you'll always get canceling going on. So 3 and a 9 would be 3. So then I have 10 times 3 times 7. So that's 30 times 7 is 210. So no matter how you do it, if you don't like the canceling, then at least cancel the higher number, at least cancel those. Those will cancel. And then you're left with 10 times 9 times 8 times 7 divided by 4 times 3 times 2. But anyway, there's 210 ways to do that.
Okay.
And then they combine that with probability. So the probability, they'll say, what's the probability that we choose any one group? And again, I'm just doing this because you're going to be asked this, so I'd like to go over it. Well, there's just one way to get any group, one way to pick any, not any certain group. It didn't say the one that had Susan in it. Okay, so there's just one way to pick any group over the 210 total ways. So besides asking you how many ways to do something, then they'll say, well, what's the probability of that? Well, there's just one way to do that. Oh, and then just one last thing. I meant to do this. Remember I talked about the complement. So if you see this, it's probability that you get at least one is 1 minus the probability that you get none. So like if you're picking a ball, I mean, that's you either get one of these or, and that's the whole sample space, or you don't get anything. So the probability that you get at least one is 1 minus the probability that you get none. You're going to use that complement formula in the binomial distributions. And for the binomial distributions, I show you how to use Excel. So it's really simple to do it in Excel. You don't have to figure out the combination formula, and you don't have to go through a big long thing. I would just go ahead and use the Excel command, and that will always get you where you want to be.
Okay.
I don't think he used that formula anyway. I'm looking, you don't use it. Let's see. Trying to. Yeah, you won't have to use that. So I don't know. That's all I have to say.
Okay. Okay.
So again, if you run into anything, I know this was a lot. There is a lot. If you run into anything though in your assignments, just please don't hesitate to ask me.
Okay. Sounds good. But thank you for going over. It always helps.
Yeah, and I'm sorry about collaborate. Like I said, I emailed the help or the IT, so hopefully I get an answer tomorrow. But yeah, I logged in. I can't get on either.
Okay. Okay. Well, you have a great Sunday evening.
Okay, you too. And I will figure out how to post this so you'll have a recording.
Okay. Thank you so much. I appreciate it.
All right, good night.
Good night.